Obviously, one of the major impacts of using energy is changing the atmosphere. We've talked about CO2 and the very, very difficult problems about the atmosphere that are associated with using CO2, with using fuels and generating CO2. Another enormous problem that is connected with that is changes in the nitrogen and sulfur cycle. We might call this acid rain, but it's more complex than that. So we are fortunate in having on our own campus Dr. Myron Mitchell, who I think without any question is one of the world's real authorities on these issues, especially on nitrogen. So, Dr. Mitchell, you're on.
Thanks, Charlie. As Charlie indicated, that acid rain is a bit of a misnomer, but it's certainly common within the lay literature. And a better term is really acidic deposition. And acidic deposition includes the atmospheric inputs of both wet and dry materials. We all know about the wet materials such as rain, sleet, snow. We have acidic materials that come in that form. This is wet deposition. But we also have materials that come in the form of dry as well. These would be gaseous materials such as nitrous oxide, sulfur dioxide. It can also be particles of material. There's actually a great deal of interest of fine particles in particular because it relates to not only acidic deposition, but it's very important with respect to human health. So a lot of these areas begin overlapping. We turn to look at the most important acid with respect to acidification inputs. These are carbonic acid, and carbonic acid actually is also generated by natural processes. If you take carbon dioxide and water and dissolve it, you get carbonic acid. The same thing you're going to find within your soda. The CO2 gets pumped in these systems at high pressures, and this causes carbonic acid. But we also have CO2 in the atmosphere, and this CO2 in the atmosphere is in equilibrium with water in the atmosphere, and this forms carbonic acid as well. We also have what is known as strong mineral acids, sulfuric acid, H2SO4, and nitric acids. And these are generated by both natural processes as well as by anthropogenic pollutants. And these are the ones that people talk about acidic deposition are often thinking about. Sulfuric acid and nitric acid. As you're all aware, acidity is often measured on a pH scale. Just give you a feeling of what that pH scale looks like. This is looking at, in terms of this particular axis, this is pH going from 0 up to 14. You actually can have negative pH as well. And this is the units in microequivalents per liter. So here we're moving with respect to more and more higher concentrations of hydrogen ion, and here we have lower concentrations of hydrogen ion. If we take a look at a pH of 7, this is actually called neutral pH, and this is where hydrogen ions equal the exact amount of hydroxide ions. And this would be if you actually had distilled water. If you actually have rain and natural CO2, you get pHs maybe around 5.7. So that's kind of, even natural waters, in terms of pure natural waters, would be acidic. But you can have all kinds of other things, the compounds, which can affect whether waters are acidic. You can also have materials which are quite basic in their nature. This is like ammonia here. Ammonia, which is used in normal household cleaning. Ammonia is also commonly used as a fertilizer as well. But other things you can be aware of, vinegar, lemon juice, also these are other acidic compounds. If you look at acidic deposition, there are a number of processes. This is looking at an urban setting, and you can see that there are, looking out here, there's natural sources. Trees, animals give off carbon dioxide, and this can contribute to acidic materials. Also, they can give off nitrogen compounds and some sulfur compounds as well. These materials which end up in the atmosphere can be redeposited. Here's dry deposition, here's wet deposition on the surfaces. And there's various sources. There's mobile sources. One of the major sources of nitrogen is automobiles and trucks, other types of mobile sources. There are also stationary sources. Important stationary sources would include such things as electric utility industry. Burning coal produces sulfur dioxide. The sulfur dioxide is converted into sulfuric acid. And also small urban stationary sources. So a whole range of different sources which vary in terms of magnitude of putting out acidic substances and this varies in terms of also the spatial and temporal variation of these things is considerable. An important part about acidic deposition, you have what are known as anions. If you don't know what anions are from your basic chemistry, what's an anion?
A negative.
Negatively charged ion, that's exactly right. So we have acidic anions such as sulfate and nitrate, and these things are mobile. That is, they move through the environment, they move through soils, they move through vegetation. And associated with these anions are also cations, positively charged ions such as calcium, magnesium, and potassium. And these particular elements are important nutrients. When we start looking at acidic deposition, it's more than just looking at an acidification issue. It's related to the overall cycling of elements and the importance of the cycling of these elements. You also have acidic cations themselves, hydrogen, aluminum. These may be mobilized in soils and surface waters, and these cations can actually be toxic. Aluminum may be toxic to aquatic fish and to terrestrial vegetation. So if you actually mobilize things such as aluminum, monomeric aluminum, this is bringing about toxicity of both terrestrial organisms as well as aquatic organisms. To show you how this works, you have acidic deposition. Sulfuric acid includes sulfate, nitric acid includes nitrate. You can also have other mobile ions such as bicarbonate ions. And as these negatively charged ions move through the system, there has to be some kind of a positive cation associated with them. There's some very simple rules and facts, if you will, in regards to chemistry. You need to have charge balance, that is, plus has to equal minus in all systems that equals. Sometimes you can have small discrepancies, but these happen over very short periods of time. Lightning results in an effect. And also you have to have mass balances. We're going to talk about charge balances. If you have a soil which is rich in calcium, magnesium, and potassium, when this nitrate and sulfate move through these particular systems, it's going to move these calcium and magnesium compounds along with them. If these are in high amounts and not in limiting concentration, this is not going to have a problem. On the other hand, if these are in relatively small concentrations, and these are important plant nutrients, they are important plant nutrients, there's concerns that the movement of these anions are going to cause the depletion of these cations, these nutrient cations, from the soil, and this can result in nutritional imbalances, nutritional problems, particularly related to calcium and magnesium. The overall balance of these varies from place to place. If we went outside of here right around Syracuse itself, we'd find out these soils are very rich in calcium and magnesium because there's a lot of dolomitic limestone in this area. So these soils are very, very rich. On the other hand, if you went to other places, went to the Catskills, down in southeastern New York, went to the Adirondacks, you would find out that in many places these are relatively small abundance, and there's more of a predominance of the acidic cations. Acidic cations such as hydrogen and aluminum. So in the same situation where you move the sulfate, nitrate, and bicarbonate through the system, you may move and mobilize these materials. These materials result in acidification of soils and surface waters, and also aluminum +3 is toxic to terrestrial as well as aquatic vegetation. There are other kind of issues related to acidic deposition. There's the degradation of materials. If you have a lot of limestone buildings, you put a lot of acid on these buildings, you have limestone sculptures, it's going to cause a degradation of these particular materials. I'll talk about this a little bit more later on. Some of these acidic pollutants interact with other pollutants such as ozone, nitrous oxide, and hydrocarbons, and therefore there's a whole mixture of atmospheric pollutants which can contribute to atmospheric degradation. There's concern that increase of fixed nitrogen to aquatic systems, and particularly to coastal marine systems, are resulting in large amounts of eutrophication. There's areas such as the Gulf of Mexico, which now have very large areas in which there are large amounts of eutrophication, large amounts of oxygen depletion, causing major environmental problems. More locally, off the Long Island Sound, there's also the same kind of problems are occurring. There's also concerns related to how these elements interact with other components of the ecosystem, the biota, and there's issues related to how this affects biodiversity, and there's linkages to the carbon budgets, and I'll talk about that a little bit later. Just to give you some background with respect to patterns in sulfur and nitrogen emissions, I'm going to show you some slides. And just to show you some of the historical information, this is looking at millions of tons of SO2 emissions within the United States, going back from 1900 up through about 1995. And you can see this pattern of general increases with some decreases. This is obviously associated with the Depression. This is associated with some other economic downturn, this rapid increase up to 1970. And then there's been a relatively steady decrease up to here, and it suggests that decrease, depending on what kind of legislation will be enacted in the future, whether that's going to be sort of plateauing or it's going to go down further, is unknown. But you can see there's been a fairly striking difference associated with SO2 emission patterns. And the peak was about 1970 in the United States, and it's been going down fairly steadily ever since. And it just shows you the actual 1980 to 1995, some of the major sources of SO2 emissions. Phase one, this has to do with some legislation designation, is electric utilities. All of the utilities are shown in green. And you can see that over time there's been a decrease. And actually some of the major decreases already occurred before this. As I said, the peak was in 1970. You can see that actually utilities are the major source of sulfur dioxide. All of the sources are relatively small. And there's been this steady decline of these emissions. To show you there's a striking spatial distribution of these emissions, you see that the largest amounts of emissions have been associated with areas within the Ohio Valley. This is Ohio, this is Indiana, this is Illinois. Major decreases, this is New York, smaller amounts of decreases, but the absolute amounts are also less. This is Pennsylvania. So the actual amount of sulfur dioxide emissions varies from region, with the most amount being taken in the central part of the United States, and there's been a general decrease in most regions. Now, one thing that happened, there was a legislation passed a number of years called the Title IV. And there's a lot of controversy about this. This had a lot of implications about some future environmental legislation. The controversy about the Title IV provision was that there's going to be a reduction of SO2 emissions, but there's also going to be an allowance of trading of emission allowances, which meant that utilities could trade, actually anybody could trade these allowances. That is, if you actually had a plant someplace within the western part of the United States, which you could reduce the SO2 emissions relatively cheaper, you could actually buy those, you could actually sell those reductions to someplace else where it would be more expensive to bring about those reductions. And of course the concern about that was that it's just going to allow people to buy off the environmental problem. That is, it's going to cause some major issues in terms of, there's concerns that the areas that are most affected are not going to result in a great deal of SO2 emission decrease. What happened though during this particular process was that it was originally estimated that the legislative mandate of SO2 emissions was going to cost $4.9 billion. With the actual use of this market-based approach, the actual cost was $2 billion. So the net savings to the American economy, if you will, was $2.9 billion. That's not chicken feed. That is a lot of money. Another thing that happened about this, which is surprising to a lot of people, probably also to myself, in that the Phase 1 utilities were 39% the legislative mandated emission levels in 1995. That is, they were ahead of schedule. So bringing about this market-based approach saved a lot of money, and also actually the actual reduction occurred at a more rapid pace. Now there's concerns, there's other legislation, some associated with carbon dioxide emissions, and there are a number of groups which are also suggesting something like this could also be done for carbon. But of course now we're looking at something different. We're talking about international trading versus national trading. We could maybe at some point in time talk about the benefits and also potential problems associated with that. But because of the success of this in the United States, there's a lot of people, especially policymakers in Washington, that are really going to stick their guns into wanting any type of international legislation to allow for trading. So they saw how successful it was for sulfur dioxide. The actual acid rain legislation that was passed like 10, 15 years ago really tackled sulfur dioxide emissions and therefore sulfate deposition. They recognized that was the major component of acidic deposition, and also recognized because it was utilities, it was fairly easy to go after. much more difficult to go after people that run everybody's individual cars. And the major source of NOx is from cars, so there hasn't been a great deal of mandate in terms of changing that. There's legislation under consideration right now in Washington that's going to be doing that. But you can take a look at this particular figure, and this is looking at NOx emissions, and you can see this has been fairly flat. Fuel combustion, this is transportation, this is us. Everything's us here, really, when you think about it. Whether it's transportation, industrial, miscellaneous, other kinds of fuel combustion, electric utilities, it's all related to our economic machinery. So let's take a look. I've been looking at kind of the emission component. Now I'm going to look at the flip side of this. That happens when this material hits the surfaces. And this is looking at a couple of figures. This figure is looking at pH across the United States. It's pretty easy to follow this. The green is low pH. The high pH, excuse me, around 5.3. The red here is around 4.3 is the low pH values. Low pH is acidic, high pH is less acidic. And you can see that the lowest water, this is looking at wet-only precipitation, is found within the northeastern part of the United States. Relatively moderate pH is found in the western part of the United States, also within the southeast. What are some of the major components of this? One of these is the sulfate ion shown here. This is sulfate deposition in kilograms of sulfate per hectare per year. These are values greater than 27. These are values less than 3. And you can see high bullets associated, for instance, within the Ohio Valley. Hot spots, this is near, looking at Tug Hill, actually. Some areas down in the Smokies in the southeastern part of the United States. This is looking at some other components. This is looking at nitrate ion, same kind of thing, greater than 20 nitrate kilograms per hectare, less than 4, same type of pattern, higher amounts within the Ohio Valley. Here we're looking at New York, this is looking at the Adirondacks, we're looking at the Catskills, and this is finally looking at total wet deposition of nitrogen for both nitrate and ammonium, shown here. High amounts again in the Ohio Valley, some high amounts again associated with the Adirondacks, some high amounts actually down in southern Illinois, southern Louisiana, I mean. So what are some of the patterns? And this is typical. This is actually from a station in the Adirondacks operated by the College of Environmental Science and Forestry. This is an NADP NTN site, National Atmospheric Deposition Program, National Trends Network site. Sulfur deposition, 1979 to 1998, I think, showing a decrease. Throughout the northeastern part of the United States, there's been a steady decrease in sulfur deposition. Exactly what was wanted to have happen associated with the legislative mandates for decreases in SO2 emissions. Nitrogen deposition has pretty much been flat. Has been any market increases nor any market decreases. Something that wasn't expected, however, was during the same time period, some base cations, and most notably calcium, has also declined. So there's been a decline of sulfate, there's been a decline of calcium. What this means was there was a decline in acidifying substances, but there's also a decline in substances which actually consume acidity as well. And this has resulted in some interesting responses of ecosystems to acidic deposition. One thing that's important to start looking at this type of information is to recognize that there's different time frames. Some things, you actually make some legislation or do something which actually results in a change in the pollutant. Some things happen very quickly. For instance, like if you look at something in terms of changing atmospheric concentrations, the actual visibility, acute health issues, those things can be dropped off in mere days or weeks. You have other things such as episodes, and in aquatic systems you can actually have certain things which occur over short periods of time due to snowmelt, and you can see that those occur over days or weeks. Other things such as chronic health effects, those can take years to occur. Chronic aquatic effects can take years to occur. You start getting into what's happening in terrestrial systems in terms of soil nutrient reserve, forest health, decades and centuries. So the time spans vary with what system you're looking at and some of the overall effects associated with that. We take a look at the surface water response, which is kind of in the month or maybe year kind of fashion. Looking at sulfate concentration. Looking at sulfate concentration in Biscuit Brook and Lake Roundance in New York. you can see we've had a decrease in SO2 emissions, a decrease in sulfate deposition, and a resultant decrease, this is microequivalents per liter of sulfate in these waters. So a direct response to changing of SO2 emissions. On the other hand, as I said before, base cations have also gone down. Some of this has resulted to actually change in sulfate, but some of it's also associated with changing in base cation inputs. Base cations would be calcium, magnesium, potassium, sodium. So what's happened is, in some cases, the pH of these systems has remained relatively low. That is, the recovery of these systems to acidification has been relatively modest. There's a term called acid neutralizing capacity, and acid neutralizing capacity is just nothing more than the capacity of the water to take up acid or to buffer acids. And you can see that the ANCs of these systems has not really gotten much different. And actually, low ANCs like 0, -25, these are kind of ANCs which can result in some aquatic issues related to aluminum toxicity. You want ANCs 50, 75. So when the ANC starts dropping down to 0 or below 0, you start having some major problems to the biota. So kind of some summary, lakes and streams in parts of the United States, particularly the eastern part of the United States, have shown substantial decreases in sulfate, but also base cations have also decreased. And this is related to the reduction in atmospheric emissions and deposition of these materials. However, the acid neutralizing capacity, that is the capacity of these systems to buffer acids, has not often shown a great change. And it's actually at these low pHs and low ANCs which have been deleterious to the aquatic biota. Yeah, Charlie.
So what you're saying is that of the incredible billions and billions of dollars we spent to clean up acid rain, that the effect has not been particularly large because the people who wrote the legislation hadn't taken Chem 101.
No, I wouldn't say that. A lot of people did not recognize that, a reduction of acidic deposition was going to also result in a reduction of base cations at the same time. And why did that occur?
But they didn't think about that.
That also includes a lot of scientists as well. This is not just a bunch of policy legislators.
But this is a Chem 101 problem, Myron. This is why
this is more
take Chem 101.
Well, where did the base cations come from?
Initially, I don't know. They put limestone in the flue to take out the as a flue cleaner, or
yeah. Most likely scenario that people are talking about is that they cleaned up the coal. And coal, when you actually burn coal, you emit a lot of base cations at the same time. So when you're burning coal, you're not only putting sulfur dioxide in the atmosphere, you're also putting calcium and magnesium into the atmosphere at the same time.
And uranium, more uranium than a nuclear
mercury as well.
plant. Mercury from coal.
So an unexpected, but possibly predictable, if you would have thought out the whole system,
There you go.
would have been that the calcium and magnesium also decreased. Yeah.
Are there any elements that you can combine with the emissions that would benefit the atmosphere, or no?
Well, it depends on what you're talking about. Some people would argue that, for instance, the actual sulfur in certain areas of the world, sulfur can be a limiting nutrient, is resulting in increased plant production. Nitrogen, which we'll talk about as a problem, I mean, my goodness, nitrogen is used in tremendous quantities across the world as a fertilizer because most terrestrial systems will benefit with greater production at the addition of nitrogen. So nitrogen, which is a component of acidic deposition, if in terms of actually feeding the world, we need to use nitrogen fertilizers to feed the world. There are some sensitive areas. An area that I work in is in the Adirondacks in the northeastern part of New York. This area composes 2.5 million hectares of New York. And just some reports, NAPAC reported in 1998. Within the Adirondacks, there's been little recovery of surface waters from acidic deposition. An EPA report in 1995 said additional reductions of sulfur and nitrogen deposition required to recover sensitive Adirondack lakes. So there's certain areas, and there's a lot of interest, particularly in New York, because of areas such as the Adirondacks as well as the Catskills have actually shown a little recovery. There's been other areas in the United States that have shown much more marked recovery, so some areas in Pennsylvania, for instance, and some areas in Maine. In terms of aquatic biota, acidic deposition has long-term effects to fish populations. Well, well-documented declines of fish populations, North America and Scandinavia associated with acidic deposition. In some cases, the fish can migrate to less toxic areas. This tends to be a short-term solution for the fish, and long-term problems certainly exist. There's a lot of discussion about what systems are most deleteriously impacted by acidic deposition, and actually you start looking at terrestrial systems, the evidence is less strong than for aquatic systems. There's suggestion that acidic deposition is affecting high-altitude red spruce populations, both in the Adirondacks as well as southern Appalachia. And there is also some evidence of a few other linkages with some other tree species. But there's a lot of things that are happening right now which people are beginning to think more and more are linked with air pollution effects. But air pollution is beyond just acidic deposition. It also includes like ozone. To understand this, particularly in terrestrial systems, you have to start thinking about the role of acidity, the role of nutrients. And this particular figure shows you what's happening in terms of soil acidity. If you actually have some soil acidity increasing over here, it's not much of a problem for plants, and actually there can actually be an enhancement of plant nutrient uptake. On the other hand, if you keep on getting lower and lower acidity, what happens is that the plant capacity for nutrient uptake begins to decline. And at some point in time, actually, you start getting a positive feedback in that the decline of nutrient uptake results in greater soil acidity, and soil acidity generates less plant uptake. So you can have a potential scenario of declining plant communities. To look at some of the global issues, in North America, sulfur dioxide emissions and sulfate concentration and precipitation have been declining. If you look at Europe, SO2 emissions and ammonia emissions, ammonia is a much stronger important component of emissions in Europe than in the United States, have also been declining. I'd also point out that the background emissions in Europe were about 4 times higher than in North America. So we're looking at a much higher loss rate. One of the major reasons for the market decline in Europe was based upon not on any type of legislative mandate, but on something else. Do you think what that might have been? What happened, do you think, in terms of the Soviet Union? What happened? When the former Soviet Union became no more, there was a marked decline in emissions, particularly from Eastern Europe, because there was a tremendous shutdown in factories such as in in the Czechoslovakian Republic, within places like Poland, within actual western parts of Russia. So there were some political reasons, former East Germany. Some of the decreases were associated with just the overall decline of the economies in those areas. There's also some legislation in Western Europe which result in decline as well. On the other hand, if you move to another part of the world, that is Asia, the emissions of sulfur dioxide and nitrous oxide are increasing rapidly. Not as they were a few years ago, as the world economy has begun to slow down, but certainly at high amounts. Industrial pollution in Asia is actually a little bit behind that, particularly of Europe, because the use of coal has come relatively late, and also therefore the sulfur emissions are relatively low. But you can even go back to the 18th century, look at breweries in Bangkok, and there's actually documentation of local air pollutions in Asia. And this just shows you some long-term historical data from Japan, looking at pH 1935 through 1955. There's a break here in 1987. Here you can see pH is 5.5, 6.0. Now we're getting pHs 4.5, quite low. So we see increasing documentation in Asia of acidic deposition showing up. To place this in a global context, this is looking at global sulfur emissions from different regions of the world. North America, South America, Africa, Europe, and Asia. So look at North America. This is the black bar is 1980 emissions. The white bar is 2020 emissions, assuming that per capita emissions are constant. Just look at population growth, that is. And the red bar is assuming that per capita emissions increasing based upon some regional scenarios in terms of increased energy utilization in these countries. You can see within North America, from 1980 to 2020, that fairly steady. And actually, probably that's going down, because actually the per capita emissions is actually decreasing. South America, a marked increase. compared to what had happened in the past. Africa, market increase. Europe, higher than in the United and in North America, but beginning to plateau off and actually possibly starting to decrease. On the other hand, the bar on the right hand, my right hand side, shows strongly what's happening in terms of Asia. If we just had a per capita emissions being constant, it's not a very striking number. On the other hand, if the anticipated growth in energy demands, and certainly see that's what's going on right now in Asia, goes up at any kind of reasonable values, you can see that the SO2 global sulfur emissions in Asia will swamp the rest of the world. This is just for sulfur, but you can do the same thing for nitrogen, you get the same reason. It's also based upon high fertilization use as well for nitrogen. Right now, actually, a lot of people are spending a lot of attention on nitrogen. Actually, there's an international conference held on nitrogen in Maryland this past October. And one thing that you should be aware about is that particularly nitrogen is tightly linked with other elements, and carbon is important linkages. And that's the reason, for instance, nitrogen is placed upon a cornfield. You place nitrogen in a cornfield to grow more corn, actually create production. There's a tremendous amount of nitrogen utilization. Nitrogen is a particularly interesting element, and there's a person at the University of Virginia, his name is Jim Galloway. He's actually chair of the environmental science department there, and he spent a lot of his life looking at nitrogen. And the concept which he likes is kind of what's called a nitrogen cascade. And the idea is, if you think about a pollutant ends up in the atmosphere, and this pollutant has some type of effect. But one thing that's particularly interesting about nitrogen, the same nitrogen atom, as it goes through different places, has a different environmental effect. That is, the same atom, as it moves to different parts of the ecosystem, affects different parts of the system differently. For instance, we have gases. We have N2O, we have nitric acid vapor, we have NOx, NO2, and NO, we have ammonia. So these gases can be derived from the combustion of fossil fuels. There are also some natural emission sources. But these gases, such as NOx, can have a great deal of impact on smog formation and visibility. If you have a lot more NOx, you're going to create a lot more ozone. And ozone is an important atmospheric pollutant. You also produce things such as N2O. N2O is a long residence stratospheric gas. And this acts like CO2 with respect to heat trapping capability, but it has a much longer residence time than CO2, and therefore it actually can contribute to global warming. Some of this NOx and ammonia, as we just talked about, can be deposited onto systems. And if it comes in as nitric acid, it's going to result in acidification. Acidification of terrestrial systems, losses of base cations, the same nitrogen. This nitrogen can also pass through to aquatic systems, to freshwater systems. The same nitrogen atom which results in acidification of a terrestrial system can also result in acidification of other systems downstream. This nitrogen can end up being in coastal marine systems, the Gulf of Mexico, off the Hudson into Long Island Sound, resulting in coastal eutrophication. So the same nitrogen molecule, which actually maybe came out from combustion of a gasoline, maybe the nitrogen started out as some type of fertilizer for a crop, maybe for somebody's lawn, can have a number of different deleterious environmental consequences as it moves through these particular systems. Also, nitrogen and carbon are intimately linked. It's been suggested if you increase the amount of nitrogen loading to some systems, that it's going to sequester more carbon. It's well known within North America, right now it appears that North America is a net carbon sink. And it's been suggested one reason that North America is a net carbon sink is because of its high nitrogen availability. The high nitrogen loading has resulted in greater carbon sequestration. There's also some issues related to the historical changes in forest cutting and other practices which result in forest regrowth as well, which may be as an important story as the nitrogen story as well. So where do we go from here? Obviously, we need to actually understand how our environment is changing. And there's all kinds of surprises. We think we know what's going on. We think based upon historical records, we think we can predict the future. We're often surprised, particularly with regard to some nitrogen issues. Our understanding of how sulfur affects systems is much greater than that associated with nitrogen, but there's a tremendous amount of work going on with respect to nitrogen right now. They're increasing attention with respect to nitrogen and carbon, getting more and more attention, how these elements interact with one another. A lot of legislative interest right now because the Clean Air Act amendment is currently up for renewal in Congress. So a lot of things are going on in Washington. For further information, there's a web page by NAPAP, if you might want to look at it. It has actually some of these slides actually came off of that web page. That's for some information. There's also, if you want to get some of the more recent information on acidic deposition, there was a conference held in Tsukuba, Japan in summer before last. And there are, just to show you the kind of stuff that comes out, this is from one conference on acid rain. These are the 3 volumes of papers. And the thing that's interesting about this particular conference, all of the other international acid rain conferences have been held either in North America or in Europe. And this is the first conference to be held in an Asian country, an acid rain conference. And a lot of these papers are Asian papers. There's a lot of attention going on in Asia regarding that. So take a look at that. And if you have any questions or I can help you with, send me an email or come by to see me at the glad to talk to you. Thanks.